package. Now we'll look at creating a through-hole package and also look at creating custom ICs. Yeah, and then tomorrow with the the double classes tomorrow, we will be looking at a rather complex PCB design, and we'll go through the whole PCB design process from start to finish with that. And that'll be in preparation for the exam project that you will be getting. And we'll also just speak a little bit about the exam project tomorrow. But yes, right. So first off, I attached my board. I attached everything to my board that all the components of my board has been successfully soldered on. And I have checked the connection, and I'll just share my screen because there's the, I connected the other camera, so you can have a look at the board and the connection, all the components populated on it. And then we'll just speak quickly about what it looks like. Right. So I'm sharing my screen. And this is the underside of the board. As you can see, everything looks to be makes good connection. All of the, so what I did do is once I've soldered the board, I check the connection on the one side and then check the connection on the component itself. And this is what the top board looks like. All the components, the switch, my ICs, the one lone resistor, my LEDs, and my resistor banks all attached and all looking quite nice. And so how did I test if my components, there is a connection? Well, I used my little multimeter, and whenever you probably know this, you attach it to one side or the other side, and then it should make that little beeping noise telling you that there is an electrical connection running through the board. Now, so like for the moment of truth, once again, this is my power connector. So I attach my battery to my board. And this happens. Flip my switches, and there's not really a big changing, but this is not what it's supposed to do. So this is supposed to be a double full adder, whereas when all the switches are off, there should not be anything showing there. And then once we switch flip the switches, it should act according to the truth table. Now, what went wrong? Did we make it a design error? But one of the main errors I feel, see if I press my LED, you'll see if I press on my finger, it goes on. And that is a big indication to what goes on. So this goes back to getting my board, populating it, and testing what everything works. Now, I did pre-test all of my devices. That's probably where you start. You have to make sure that everything, that all your components that you are using, they do work. And I did test all of them beforehand. How did I test them? Well, I created very small logic circuits on the breadboards and just made sure that they did work, because it's not that complicated of a circuit. Then I checked all of my soldering connections. So I did have a very hard look at my soldering connections. They do not seem to be the problem. The next thing I did check was, obviously, I tried to, just to make sure they make contact as well, especially with the IC sockets I'm using. I tried to take out the ICs. So on the socket itself, I then removed and the ICs, checked if all the legs and everything was still intact, and then replaced them. And then made sure that they were sitting correctly. I can replace this one as well, making sure that they are all have the correct orientation. And that did not seem to be the problem. Now, the next test that I was, like I said, I pressed my fingers on these components. What does that do? I made sure that's just to check the electrical connection. And as I was pressing down, I saw that this LED lights up if I'm pressing it, which means somewhere there is a electrical connection that does not make a very good connection. And the reason for that is that I made a sort of like a design error, and hopefully I can explain this error so that you understand what I did wrong. Right, I'm opening EagleCAD. I'm sharing my screen with you guys so you can see my EagleCAD screen. Right, so this is our adder, right? And we switch it to the board, and this is our design. Now, I decided to have the connections both on the bottom side, which is the blue side, and the red on the top side, right? So I decided to make a double-sided board. But as you can see, I only soldered on the bottom side because I have through-hole components. I stick the components through and soldered on the bottom. And I did not solder anything on the bottom. So how these connections work, these connections, if I have a through-hole connection and it's connected on the top and bottom side, that means I have to solder on both sides. The holes aren't connected. They are not a via, which is connected. There are simply electrical connections on either side of the board. So if I have a through-hole component, I need to connect it. I need to add solder on the one side and then solder on the other side as well. So what is happening first and foremost to my board is that I only soldered on the one side. And I did not add any solder on the top side. That is why when I wiggle around my one LED, which is for reference, which is this LED, LED 1, the green LED 1, and which you can see they are both connected on the top side, and I've soldered it on the bottom side, meaning that it does not make connection at the top. The other LEDs, which do make better connection, have some connections on the bottom side. So that is probably my biggest mistake. Now you will ask, well, okay, great. So that was your mistake. Why don't you just add solder to the top side? Well, that is a little bit easier said than done. With components with longer leads, it is easier. Like I'm just showing my screen again so I can talk about that. So with components with longer leads, like the resistor in the middle, sure, that is easy. Also, this component here, that is also not a problem. The problem comes in components like this switch over here, my switch. So as you can see, there is not a big area for me to add a solder. Same with my ICs, the socket I'm using. There is not a big distance between the IC socket and the board because they sit so closely, because they sit so snugly and close to the board. I cannot get a soldering iron to solder those connections. So now I've a big problem. I have components that I need to solder on both sides, but I cannot solder these. Now, I can try and solder them by using a very, very thin soldering point, but that is very difficult. And quite often than not, we will burn the components. Because that little point, it adds a lot of heat on a very, very small area, and I need the whole pad to heat up along with the component leg. So this is an example of a design that works, but cannot be constructed, implemented, and assembled correctly. So once again, my biggest problem is that I have connections on the top side and the bottom side, and I only soldered on the bottom side, and I could not solder on the top side because my components, especially the IC, the switch, and also the LEDs, the one LED specifically in question, this LED is also really snug, and I can't really get to the leads on the top side. As well with the resistors, probably not that much of an issue, but it's still relatively hard to get to those. So I made a mistake in my design by not foreseeing that my components that I'm using will make it difficult to solder on the top side. So what should I have done? Well, I should probably only have had my connections on the bottom side. That is probably the biggest or the easiest way that I could have created my circuit, was just by having connections on the bottom side. That is definitely something I could have done. Another option would have been to have something which we call through-hole plated connectors, meaning that if I have a connection and there is a connectors running on the top side and the bottom side, then there is it is coated with metal on the inside, meaning that both the top side and the bottom side are connected. I did not do that, but if you do that, it does cost extra, and it does takes longer to manufacture. So now I have relatively two options. Well, there's also a third option where I just spend a lot of time and thinking about how I'm assembling my board, and first put in the components a little bit, like halfway, solder them on the top side, and then soldering them on the bottom side. So first soldering where the components are most difficult, in this case the top side, and then the bottom side. But then as well, my assembly time will take a lot longer. So yes, my board does work and I can make it work, but the biggest takeaway that you have to take from this little lesson is that you have to think about how your boards are going to be assembled. Now, the issue is that a lot of my ICs lay flat on my board, and that means I cannot solder them from the top side. So I see a lot of PCB designs from students who just use the auto router, and the auto router does not care what your component looks like, how you are going to be, how you assemble your components. It does not care. It it just connects up the components. It does not care how you're going to be assembling them. But just make sure, like I have not done, that you think about how to assemble these boards. Because, I mean, I will fix this board, but it'll take me a very, very long time because I now have to get a very, very fine solder iron and somehow solder these ICs and these LEDs from the one side and the top side. And I might even have to remove a couple of these components and reattach them in a different way. So that is my mistake that I made. So once I fixed the board, I soldered on both layers. Then I will then test my board and test the functionality of it. If it still doesn't work, then I'll use my multimeter to check the voltage levels. And then I'll go back to my schematic, see where my logic levels, what they should be, and then also then what they actually are, which might be a different thing altogether. So yeah, so this was an exercise on what not to do. And like I said, I just used the auto router. I clicked on top and bottom, and I didn't really care about where it was, how it connected. I just cared that it was connected. But then again, when I came to manufacturing, I had a problem because not all my components can be soldered on the top side and the bottom side. Well, they can, but very difficultly. So this is something that you have to think about when you're designing PCBs. Now, if you're designing a PCB as a one-off and like a prototype, then this might be fine. You will be fine. You'll find a way to attach both components on the top side and the bottom side. But if it's a PCB that will be manufactured in a bigger batch or a bigger series, like a couple of hundred, then that will become a major problem. And I've had times when I made a very dumb design, which is very hard to assemble, and that design was given back to me by the assembly department, telling me that this will take too long to assemble. We'll save more time by me just redesigning and then resending the door, remaking the PCB. Now, all of these problems is very hard to see beforehand, but you will just have to think about the components that you have selected and then decide just visualize how your board is going to be attached. So if I have through-hole components, and I pretty much only have through-hole components, I try and do as much as my work as I possibly can on the bottom layer, because that is easiest for me to attach my components. Because through-hole sticks through the hole, and then I can attach at the back, and it makes a connection. If I'm using SMDs, it is easier to connect on that specific layer, or surface mount devices. It's easier to connect on that one layer. And SMDs are easier not to make the mistake because they can only be connected on one layer and they have no through hole or issues with connecting to other elements. So this issue pretty much only ends up or is more prominent with through-hole components. So once again, think about through-hole components, think how they are connected to your board. And if you have a trace from a through-hole component running on the top side and on the bottom side, just be aware that you have to attach them with solder on both sides. Otherwise, your board won't make good contact like my specific LED did or does not do. And so, yeah, so just visualize your board and make sure what you are doing makes sense and that it can be assembled. And also think about, it's always good to have your components with you. To think about, okay, this is how they fit together, because sometimes some components are larger than you might expect, or might be larger than the EagleCAD visualize for you, and you just have to think about, especially if you're using big capacitors. Capacitors might be pretty big like that, and they take up a lot of space in your board. So with this in mind, you always have to think about how your components sit on your board and how you will be attaching these components. And that is why the Auto Router is a brilliant tool. It really is. But it does not take into account the ease of connection of your board or ease of operation of your board. So that's once again my mistake that I made. I used the Auto Router, just click Auto Route. It connected everything, top and bottom layer, perfect. And I thought that was going to be the end of it, but no. I needed to think about connecting components on the top side and the bottom side. Right. So that's hopefully get you thinking about, so like thinking about your boards and also taking into account the assembly process, how components are attached to my board when you start designing the board. Okay, so let's continue on with creating custom components. So I'm sharing my screen again. Right, should see a person running. Right, and this is of course EagleCAD. Now, once again, we have, we can go to new, or in this case, because we've already created the library, let's open our library. And we created the library called Class 2023. I click open. Now, once again, if you did not create your library, you simply go and make new and click on that. But we don't want new, we want our old library that we have created. Now, excuse me. Now, once again, why do we create custom components? Well, if we have components that are not available in our Eagle library, then we make them ourselves. We usually start with creating the symbol. In this case, this is what our symbol representation looks like. We create the footprint. And then we add them together. And also, if you have got a 3D representation, then you can add it there. So what is the 3D package? How does that work? Well, it is a functionality of Eagle, but it links with another software package that is mostly not free. And that is the Autodesk digital design software. Now, a lot of other projects or software do have this functionality where they have a 3D representation of a component, and they give you a good idea of what your board looks like with the components attached. Now, Eagle does have that, but you have to have the accompanying AutoCAD software. Now, we could have gotten a 1 month free subscription with that, but it doesn't really bring that much to the table, and I thought it would have been a not that useful. Okay. So once again, this is our resistor, and just as a reminder, we looked at this data sheet of our SMD, with the solder pad land pattern, and we created our 2512 code resistor for here. And this almost always you will find in some sort of data sheet. Now let's have a look at so this is a data sheet for a through-hole resistor. Now these are relatively common, and most of the time these become or are the same throughout through-hole resistors. So once again, we have resistor packages, different types for the specific resistor. Here we have a dimensions, which we probably will be using, how long the component is, the diameter of the resistor itself, and also the diameter of the pin or the lead wire. Also, they give you a good idea of coating residues. So what is a coating residue? So all of these components, the resistors, are coated in sort of like an enamel to protect them from outside interferences from the atmosphere and stuff. So a lot of the times this coating residue is not just on the component, it will also be found on the legs as well. So what will happen if I try and bend my resistor where there is still some coating residue, the coating residue might crack and break. And that crack might spread to the component. So what we generally then try and do is then bend our leads on the outside of the further away from the coating residue, so that our coating residue does not crack, and so like our component does not crack and break. So this will be our minimum distance for our leads. Now, something that's also relatively interesting. Now, this data sheet gives you all the information. So, like, it also gives you an overview of the bands that you might find, in what packages these will be. You can buy them in these reels with 1,000 of these resistors. And something that is relatively interesting is that you can use a through-hole resistor in a surface mount configuration, which when I studied, I did not know this. I thought that, well, you can only use these as through-hole. But here what they have done is that they bend the legs in this sort of fashion, and then bend this into sort of like this L-type shape. And now you can place the resistor in an SMD configuration and attach it to only one side of the board. So this is a relatively, well, it's not something new, but it was new to me when I studied. I thought through-hole components always goes through-hole, SMD components always sticks on the side, but you can have through-hole components that you create or just bend the wires in an L configuration and stick it on an SMD board. And therefore, you can then create a solder LAN pattern or create an SMD landing pattern, which they have created there, but we already created something similar. So it's just, you have to also think, so like three-dimensionally, that you can have through-hole components and use them in an SMD role, which I think is quite exciting, or interesting at least. Right, so what we're going to be doing, and once again, this is the reels. And once again, they show you so like the alternative lead configuration. So what does this do? if you order enough from this company, they can bend all the resistors for you. So they can bend this, it's like in what they call the goalpost, a little kink in it, and also what they call the radial, which is standing upright. But this is mostly for more large manufacturers. If you buy thousands from them, they can pre-bend everything for you. So this little kink, it's just so it sits nicer in the board. So you press it in, then it sort of centers itself. So what we are going to be doing we are actually going to be looking at creating our through-hole resistor with these dimensions. So this dimensions is what we're going to be looking at for us when we are creating our resistor package. Now we'll create or we'll select a resistor type. I think in our case, let's look at the RXS340. And we'll create a resistor type for that. So back on our library creation screen, we can add symbol. That's usually where we start. And we will call it our RXS 340 and resistor. Okay. Yes, we create a new one. And we have our landing page here. Now, once again, I like our measurements. In this case, they are in millimeters. Oh, no, that's not. So I will be using millimeters for my grid size. Millimeters, a relatively fine millimeter grading. But you might have seen I do not use this alternative that much. So this is our midpoint, our 0 point. And remember, we are dealing with a two-dimensional grid. So we go to our pin and we add our pin here. Well, it doesn't really matter. Well, doesn't really matter that much. Once again, this is just the symbolic pin, so we don't necessarily need to have it that perfect, because this is just the symbol. So once again, we go to info, and then we can have we can rename our pins. So let's say this is pin number 1. It's at position -10. Its direction is an input-output because a resistor can be connected both ways. Length, so like let's have a short length, and visible. Yes, that's fine. Okay. Pin number 2. Let's have it at +10. Length also short. So what that short length does is it just creates this little short length pin there. You could have, it doesn't really make a difference. What we more care about is this square circle here. So we have our pins there. And right. So once again, these are all the layers we can work at. Let's continue working on the symbols layer. And we can now draw our resistor in any way that we like. So that does not look very good. So let's create another element. We can also create a circle. It is fully up to us what we are creating. And I have decided to create my circle or my custom resistor in such a way. Now, you keep in mind that you are creating a custom component, a custom symbol. You can also reuse old symbols of other components. That is also fine. I'm just recreating it so you can have an idea. Another piece of advice that I would have is not to go too crazy with the design of your symbols, because the symbols will be inside of your schematic sheet, and other people will look at your schematic sheet or look at and evaluate your designs. And then these components will have to make sense. So if they see the symbol on a schematic sheet, mostly people won't have an idea what it does. I know it's resistor. Other people might not know it's resistor. So when you are creating these symbols, make sure that the symbol actually makes sense. Because if I'm using this symbol in my schematic, it's not a recognized electrical symbol. So other people looking at my design will not know what is going on. But for me, this is fine. And now the last thing I need to do with my symbolic creation is create the keywords names and place that on the names layer. And then as well, I don't need this. Change the bottom one to values and put it on the values layer and click apply. So once again, what do names and values do? Well, they are, think of it in a programming sense, they are variables for our names and values. So when we are using it in a schematic design, we can rename our components, component number 1, component number 2, R1, whatever, and that name will be saved in that space there. Same with the values. If we give our components a certain value, then the value will then be saved. It is relatively important that you add in these variables so that you can name your components properly. And then this is now fine, so let's save it. And then close it. Now, let's open up my library again. And now I can see my resistor symbol is there. Now I can add in my footprint. Let's call it the RXS 340 resistor through hole. TH through hole. Create a new one? Yes, I would definitely like to create a new one. Now here we have to be careful what grid we're using. As we spoke about, let's use the 0.1 grid and 0.01 for my secondary. And just remind ourselves what we are dealing with. So we have our diameter of our pin. So if we put down pads, our hole has to be a diameter size of small d 0.8. So our RXS 340 has got a diameter of 0.8. Right. So that is what my component should, the minimum size for my hole. Now, usually you add in just a little bit of room because you add in a certain tolerance. Now, I usually go with a 10% tolerance and then round it down. Why do we add a tolerance? Because if you make the hole in your PCB design exactly as big as the lead, you might have some problems fitting the lead inside of the hole. Why would that be? All these components and the PCB as well, to a lesser extent, are mass manufactured and all have certain tolerances. The lead tolerances in this case, if I'm sharing my screen, they tell you that it might have a difference of 0.05. So if we add in a tolerance of 0.0 or 0.1, then that will be a good. So this might be plus or minus 0.05 millimeters either side. And also the PCB manufacturing, although they are using very precise drills, the drill might also create a smaller hole or a bigger hole or whatever, or it might be through hole plated, meaning that the hole is smaller. So I generally keep with like a tolerance, creating your drill holes 10% larger than your than the actual diameter of the component, just so it makes fitment a little bit easier. So my diameter is 0.8. So 10% would be 0.88, but we can round down to 0.9 just to be extra sure. So we make our drill holes 0.9 millimeters. So here we select our pad. We can select the size of our pad, round, octagon, so this is what round, square, and octagon, or pads like this, or this where it's sort of like an offset. I generally go for, depending on which components, I go with a round pad, and my drill, as we spoke about, is 0.9. And I place it down here, and also here. Now, once again, the diameter, which is the diameter of the pad, is set to auto, but I can also create a bigger diameter if I want. Let's create this, see what that does. Very, very small. So now what diameter does is just enlarge the pad, adding a bigger area for us to solder onto. Okay, so let's just have a 5-minute break, drink a little bit of water, and then we'll continue on with this. Welcome back. Okay, so what we're doing now is looking at the diameter variable. So the diameter is how big your pad is. So you have your hole going through the board, and then how big is the pad surrounding it, leaving you space to attach your component with solder to that. So the bigger it is, generally the easier it is, because the easier then it is to have space for your soldering iron to make contact with that, and also the component. Very rarely do I make it custom sizes. I mean, obviously you can. Most of the time, I just leave it on auto. And once again, we can change the drill shape and what type of pad it is. So now we have to have a look at our the dimensions again. Now, once again, this L max is how long the component is. For 3/4, it is 13 millimeters. But then we spoke about those 2 millimeters on either ends with the coating residue. So all in all, it's 13 plus 2 plus 2. And that is our minimum size that our components can be. Now, I might decide 13, 2 plus 2 is 17 millimeters. That is how big I want my components, or how big it should be. But you can also have this longer, or not really shorter. There's the minimum distance. And I generally find with through-hole components, they do have flexible, bendy legs, so it's easier to design footprints for them because the components can be bent in multiple ways and at multiple distances. So for this case, let's just take 17 millimeters as our distance. So this will be the distance from 2 till this area here. Meaning this is how our component will be inserted into our design. So we have 17 millimeters. So now we have our origin. We click on info of our pad, and we can adjust our position. So 17, half of 17 is 8.5. So we shift this, the left side to 8.5. And also the right side to also 8.5. So now I have my components on either side, and they look quite a way away. But if we check our grid, check this, we can see it is 17 millimeters away, which is exactly what we want. So now the component is kind of correct. What we can do is now add in the silk screen. So T place, we worked on this. Let's create the T place, and we select a rectangle. It is a body diameter of 5.5 millimeters. So let's go from the origin. 5.5 millimeters. 5.5. And then it was 5.5. And then it was 5.5, and then it was 13 millimeters. No, not that. right, from -6 to 5.4. Right, so this is in the from our X and Y position. So this is 13. Let's just see if it fits in. Let's you can also select it as a group. Move. Right. We can also add in our names. And then also our top values. Once again, it has to have this element in there and also the values. And now I have my component selected and created for me. And once again, you can add in anything you want, but just make sure that it makes sense. So let's have a we can have a wire. Just create on this side. Right. And these are my components. Name 1 and rename this as 2. So I can save it. Now you can be as creative as you would like, but just remember that it all has to make sense and it all has to be usable. So we saved it. Let's open my library once again, class of 2023. And now I can see that my resistor, the symbol is there, and also the names is there as well. So the next step we can do, close these. The next step I can do is add a device. I call it the RXS 340 resistor through hole. I click OK. It asks me, do I want to create this device? I'm tell it yes. Now, the first thing we need to do is add our schematic design, add our part. We choose of the parts that are inside of our library. This is the one we want. We click OK, and we place it down wherever we want. Usually, we place it down somewhere in the middle. Now, you might be asking, why do I design everything around the middle? Why don't I just work in one, like the positive quadrant, to make my life easier? Well, you have to remember that when we move components around in Eagle, you usually select it at the middle or its origin. So that is why I designed my component so that the origin is in the middle. Otherwise, if it's on the bottom left, then I will have to click on the bottom left to move my component around. It's a lot easier having the origin in the middle. So that's why I design my components around the origin. So it's on the left and the right side of the origin, so that when I select it, I can just click on the middle of the component and I know that it will move around my component. So that is now here, my resistor. I can click on new, add a local package. Now you can also search a package from the web. I'm not going to do that because I've already created it. And I click on my package name there. I click OK. Now the next step you need to do is connect. And this is where I'm mapping my pins to my pads. So we can connect the 1.1 to 1 and 1.2 to 2, meaning that this pin is now connected to that. Pin number 1 is connected to pin number 1 there. Pin number 2 is connected to pin number 2 there. I can add in my description. Through-hole version of the RXS. Is the RXS? Just check the name. RXS 340. And click OK. So now I've also written a short description. And now my component is done. I can click Save. I go back to opening of my library, and now my resistor, they are both there for me to use. Now let's just close this. How do I use them? Well, let's create a schematic and look for them. So we have our add part. Now, once again, the schematic does take a while to load all the libraries. And there is our library. So these libraries are all alphabetical, so it's relatively easy to find our class 2023. And there we have our through hole and our SMD resistor. Now, the through hole, you see it does have a description. The SMD does not. So if we click on this, we can place down our component. And we can also place down our SMD component. And we can connect everything up. And we can use our components now. If we switch to our board, let's just do that for a, we can see these are our SMD and through-hole components that we have created. Perfect. So I'm not going to make this simple board. And that's as easy as it is. So the next thing that you will need to understand or get to try is creating IC packages or array pins. So if you have, now this happens more often than not. Well, it happens more often than creating a custom package for a resistor, because most resistors come in relatively good packages. I might find a component, an IC, a custom IC that Eagle does not have a package for. That happens often. So it is then easier for me to, well, if you have an IC like a 14-pin IC like that, and it is in a non-standard package, you can do one or two things. Either look for a IC that is comparable in Eagle to that, or just create your own. And we'll now quickly just go through creating your own IC. Now I'm going to be using a 555 timer as the base of the IC. Why am I using a 555 timer? Well, the 555 timer, we do have a schematic for 555 timer, but let's just create our own. I've selected the 555 timer because it's got a really good data sheet, and we can have a look at the data sheet and look at the mechanical properties of a 555 timer, and then create a custom component. So I'm sharing my screen once again. So this is the from Texas Instrument. This is the 555 timer precision. The NA55, NE55, SA55, or SE55. It gives you all of there's a simplified schematic of what it looks like on the inside, the 555 timer. It gives you all of the good information, what the packages looks like. And at the end, if you click on mechanical, it gives you a good idea of what all these packages looks like. Now, what I am more interested in are these areas. So this is a one package outline of this 555 timer. So let's create a package for this. Right, but firstly, we have to look at what the pin configuration. So let's create a schematic symbol that looks like this, with pins 1, 2, 3, 4, 5, 6, 7, 8, ground, trigger, out, reset, continuation, threshold, discharge, and VCC. So let's create this schematic in Eagle. So we go to our custom library. We open up our library where we want to create a component. We start with adding a symbol. And let's have a, oops, that is wrong. 555 timer. And yes, we want to create this. Let's create the grid, which I like to use, which is my millimeter one. 1 millimeter. Okay. So there's like a hard way to do it, and then there's an easy way to do it. So the hard way to do it is to select your pins and place down your pins in this fashion here, and then draw a block around it, something like that, and that will be your IC. There is an easier way. If you click on pins, here you have all the pin configurations. Here we have a pin array. So we click on that, and now we have a very good, we have got a tool that creates this for us. So we give a base name. We have a base name. So the base name is just what it starts with here. So we'll just call it our timer. Where do I want my pins? Let's have our pins only on the left and the right side. How many pins do we have? We have 8. include name, include value, generate a rectangle, and then click OK. And it has created our element for it, but it doesn't look that great. So let's do that again. Create my pins. Let's just call it T, left and right, pin count 8. And we place it in the middle. Now, it does not look that great. So let's see if we can move around our pins. So, and now we can name our pins to make sure we know what's going on. So we can name our pins as well, 1, 2, 3, 4, 5, 6, 7, 8. But we can also just give them names in terms of ground. So this pin here is called GND, and it is not an input-output, it is a power pin. The same with the opposite pin here. It is our VCC, and it is also a power pin. So what does that do? By designating these pins via its function, because ground and VCC are our ground and VCC pins, they are power pins. So if we connect them to a net that is not designated as a power pin, our electrical rule checker will tell us, just you've made a mistake, you've created a power line to a pin that does not make sense. So that is now where we designate the names of these pins. This one is trigger, and it is only an input. Out, which is an output. Reset, which is also an input. Fine. Discharge, which is an output. I'm not sure what discharge is, so I can leave it as input output. And this one is threshold. And lastly, we have our CONT. And once again, if you don't know what they are, just leave it as input output. Now this is a bit of a problem. Aha. And let's have this. Let's have them staggered like this. So that's a little bit better. Now, obviously, you can play a lot around with all of these different elements, but this should be fine. Now, we are running out a little bit out of time. So this is easy to create. So we save this. We've created the symbol that we can use. The next thing we can do is create our footprint. So we go to our library. Open up our library again. And then we can create our footprint. 555 timer SMD. Yes. Create our grid. Millimeters and 0.1, that is fine. And now we have a look at our SMD package type. And this is what we are interested in. Now, once again, we are going to be using the easiest way. So the easiest way to create this is as well, let's go to our SMD pins. And here we have a SMD array as well. So we click on that and we have our SMD array. We have P, it's got left and right, SMD count, it's got 8, start index at 0. So now we have a couple of variables that we would like to create. So first off, we have the SMD spacing, this dx. So this is the distance between the pins. So let's see if we can find this. So the distance between the pins or the center of the pins. And once again, we have a variable distance, meaning that the connection is between 5.8 and 6.19 millimeters. So we take the distance between the holes, or the center distance is between these two distances. So why are there two? Well, because we have an SMD connector, meaning it's relatively long, or it starts where it's made contact and then it goes into where it does not until the end of the lead. So the starting distance is 5.8 and then it moves to 6.9. So we can have the middle distance between them is 6 millimeters. So we can have a dx spacing of 6 millimeters. Oh, that's dy. Let's get to that. And 6. And dy is this distance between these two pins. And here we have the distance between these pins. It's 1.27 millimeters. So now, again, you will have to understand which unit you are using. This is inches, and this at the bottom is millimeters. So our dy distance is the distance between the pins, and it is 1.27 millimeters. 1.27. We have all of the information. We click OK. It generates our SMD element. It's got the name and it's got the value. And here we have pins P0, 1, 2, 3, 4, 5, 6, and 7. It starts at 0. We can also start at 1 if we so like. Let's actually start at 1. That's fine. Let's redo that. go to SMD, array, let's call that P, left and right. We have 8 of them. DX, we said was 6, and this is 1.27, and we start our index at, let's start it at 1. Delete the existing. If there is something existing on the board, just delete it. Create my rectangle. If I want to create the rectangle, I can always do that a little bit later. Let's not do that. Apply. And now I can place down my components with the SMD. Now I can draw in my elements a little bit later on T place, if that is something that you would like to do. Now, another thing that I forgot in my previous design, I need to create my T keep out, or the top keep out plane. And remember, the keep out zone is so that no other component can be placed within this box that I've just drew. I can save it. Open up my connections once again. Ooh, excuse me. And then I can add my device. Let's have my 555 timer SMD. Click OK, create my component, add my part from my 555 component, place it at the origin, add a local package, my SMD package, I have it there. And then the last step is to connect all of my pins. Now I have to make sure that all of these pins are connected to the correct package type. Now, once again, these are not so easily to be seen. So what I need to do is have a look at my pin configurations and see my number 1 pin is ground, 8 is VCC, and so on. So I select VCC, or let's select ground. It is pin 1, and then I connect it. Pin number 2 is trigger. Pin number 3 on pad number 3 is out. Pin number 4 is reset. Pin number 5 is this continuous. I think it's continuous. P6 is threshold. P7 is discharge, and P8 is VCC. I click connect. My component is connected. I can also write a description. The SMD package for the 555 timer. Oopsie. And I click OK. I can save it. And as we can see now in my custom library, we have a 555 timer. Now we can quickly also do the through-hole package, because that is also relatively simple. Let's have timer through-hole. Yes. As well, we create our grid to the ones we like. I just need to scroll to my Also another type of SMD package. And this is what I need. So once again, I'm going to be creating a through-hole package according to this. And then again, I also use my through-hole pins. I also create a pin array. Starts with P as well, left and right. Now, I can also have pins on the left and right, top and bottom, or just everywhere, but I do not want to. So once again, we need a dx distance, which is the distance between the center of the pins. In this case, it is between 7.37 and 7.87. So I will make it 7.6 just to have a distance in between. And remember, through hole is a little bit easier because you can bend and open up the pins. So I'll have it at 7.6. dx is 7.6 millimeters. And my dy, distance between the pins, 2.54 millimeters. .54. Let's generate everything. Right. We add in our keep out. And I don't want any components within this area here. I can also change some of the information. Let's say I want that as a square. Let's say I want this one as a round pin. This also as a round pin. So you can change any information you want on the shape of the pins when you use that wizard. I can also move the pins around again if I so wish. And let's also have this as a round pin. And I can save it. Now the last part I can do is now just connect it up. So I'm going to be using the same schematic because the schematic does not change. And have 555 timer underscore through hole. Create it. Select my 555 timer package. Add a local package, a through hole. Right. Connect it up like we did previously. I think 1 is ground. 8 is VCC. And pin configurations, there we go. 2 is trigger. 3 is out. 4 is reset. 5 is continuous. 6 is threshold. That. Add my description. Yeah, and save it. And as easy as that, we can create custom components. So we've run out of time for this lesson, but we've covered mostly everything that I wanted to cover. Tomorrow, we will look at a more complex PCB design, where we'll be creating our custom components, have a microcontroller, a relatively complex circuit, and then design a circuit from the start to the finish, and also thinking about the assembling of it. So that's tomorrow. I'm not going to take any more of your time. Hope you enjoyed this class, and I'll see every one of you in tomorrow's class. All right, because it is the last class, so it'll be fun. Bye, everybody.